In this class, let us see that a circular current loop is equivalent to a magnetic dipole. Magnetic dipole is a system of two equal and opposite poles separated by a small distance, that is north and south poles separated by a small distance. Let us consider a current loop. The magnetic field due to the circular current loop at an axial point. For a current loop, magnetic field at a point on the axis is mu 0 I r square by 2 into r square plus x square raised to 3 by 2. If the distance is very large compared to the radius of the coil, r square can be neglected, so the denominator becomes x cube, 2x cube. Let us multiply and divide by 2 pi. So this equation becomes mu 0 by 4 pi into I 2 pi r square by x cube, where pi r square is the area of the plane of the coil. And if there are n turns, the field will be n times. And Nia is the magnetic dipole moment of a coil. So, axial magnetic field is given by mu 0 by 4 pi into 2m by x cube. For an electric dipole, the electric field along the axis is 1 by 4 pi epsilon 0 2p by x cube. So, comparing the two equations, we can conclude that a current loop is equivalent to a magnetic dipole. A current loop produces the same magnetic field as that produced by a magnetic dipole, where the magnetic dipole moment of the loop is m equals Nia. The difference between electric dipole and magnetic dipole is that an electric monopole can exist, while a magnetic monopole cannot exist. Now let us see a bar magnet which is equivalent to a solenoid. A bar magnet and a solenoid produce similar magnetic fields. Let us consider a solenoid of length 2L and radius A. Let us find the magnetic field at an axial point P at a distance r from the center of the solenoid. Let us consider a small element dl, and the number of turns in this element is n dash is equal to n into dl, where small n is the number of turns per meter. The magnetic field due to this element is dB is equal to mu 0 n dash I a square by 2 into r square plus a square raised to 3 by 2, where n dash is n into dl. In order to find the magnetic field due to the whole solenoid, let us integrate dB, and the limit is from minus L to L. So B is equal to integral dB, which is equal to mu 0 n I a square by 2 r cube integral dl, and the integral dl is the length of the solenoid, that is 2L. But n into 2L, that is the total number of turns of the solenoid, capital N. So this equation becomes mu 0 n I a square by 2 r cube. And let us multiply and divide by 2 pi. So B is equal to mu 0 by 4 pi ni pi a square into 2 by r cube, where pi a square is the area of cross section. So 2 Nia by r cube. NIA is the magnetic moment M. So magnetic field is given by mu 0 by 4 pi 2 m by r cube. In the case of bar magnet also, the magnetic field at an axial point is mu 0 by 4 pi 2 m by r cube, where n is the magnetic moment of the bar magnet, which is equal to pole strength into length of the bar magnet. If we consider the field lines of a solenoid and a bar magnet, both are similar. One end acts as north and the other end acts as south. The field lines are directed from north to south outside and south to north inside the solenoid. Thank you.